All right. Can you hear me? Yeah. Again, a Teams meeting. Everybody asks if you can hear me. Yeah, good. Yeah, welcome to the OSP Conference of 2023. We must say that we are really happy that so many people could join today, and really, especially that so many people took a trip to the sunny Ålesund. As it normally is. Unfortunately, I'm not able to enjoy the sun today, but it's quite dark in here, but that's how it is. My name is Knut Ore Aurdal. I'm the head of innovation project in the GC Blue Maritime cluster. And this year, the main partners in the OSP project, SINTEF, NTNU, DNV, and Kongsberg, which is all member of the cluster, asked us if we could host it. And of course, these kind of things we are very eager to do, so that we do. So basically, we are hosting it, and maybe we could say the program is a bit more on the SINTEF Ålesund side. So then at least you know who to blame if you have some some comments. Yeah. Then this should work. Didn't. Maybe I turn it off. Yeah. I thought I should say some few words about the Blue Maritime Cluster before we start. We are the biggest maritime cluster in Norway. Even though we have companies all around Norway as members, the most of them is in this region of the maritime cluster. 170 companies and organizations hosting more than 14,000 people and have an annual revenue of 58 billion NOK. And what we are very proud of is that we are a very complete maritime cluster around here, from the startups to the shipyards, to the banks, and to the research organizations. So for those that haven't been here on NMK before, it's a very interesting spot when you look around with both NTNU and SINTEF is here, Møre Forskning, and a lot of companies like Kongsberg and others that is here today. And what we do, we are not a lobby organization. We are, as it says in the quote, we facilitate innovation development in the cluster. So we are basically working with business development. And we are hosted by OKP, Ålesund Kunnskapspark, which was a part of the original OSP project. So it's natural. So that is the link here. A little bit about the program, I should say. I could say that we've divided into 4 parts. The first part is a little bit of an insight in the use and the needs of simulation by different companies. Vard and Kongsberg will say something about that, in addition to SINTEF that will start it off soon. Then we have another part that we call inspiration and possibilities, in a way, that hopefully can grow into something. And then we have a part in the end with ongoing OSP projects. So hope it will be a very interesting day for all of you. In between here, we have lunch that will be outside in the area that we were standing there. And then as a 4th part, as we thought it was very good, or when we get so many people coming here, of course the best thing is that people can have some time to talk to each other. So then we have launched this Blue Maritime Hangout that will be outside of here. Yeah, the concept is like you hang out. There will be some food, and there will be pizza, and there will be some refreshments. And it's in the end of the day, so maybe it's more like a hang in there event than hang out, but I hope it will be good, and I hope as many of you as the possibility to stay and get to know each other, because that is where magic happens, I think. Some practical information Yeah, there is not planned any fire alarm, so you escaped the door you came in, or in the door down here to the right of me. Yeah, toilets you can find outside on both levels. We are going to record the presentations, so we will share it afterwards. Both the recording of the presentation and the actual presentation, the PowerPoint. If there's anyone that has any allergies and so on, just grab the hold of me or Ole, which is here, and that is the technical part today, and or Jan Børre, which is also standing or sitting here alone there. That is our EU advisor. So if you have any questions, just reach out. Yeah. So that's any questions before we start off? Because if not, then I think we just move on and start up. And to host us through the day, we have a guy that is probably familiar to many of you. A guy with a PhD in theoretical physics. A powerlifter and cat lover. And I read a description on him on LinkedIn naming him the best theoretical physics doctor, professional photographer, economics, philosopher I know. So in other words, a multi-talent, and he's even Austrian. So please welcome Severin Sagina. And together with him, after coming soon, will be Christian Steinsvik, which is the CEO of SINTEF Ålesund. I didn't find too many fun facts on you. So yeah, I give the word to you, Severin.
Thanks. I can confirm he is fun. Also, the irony you pointed out that we're on the one day, it's actually nice here at this time of year. We have to sit inside. It's now not lost on us. Thank you. I don't quite remember the first time when I came in touch with the Open Simulation Platform, or OSP, as the cool kids call it. But there's one thing I can tell you with 100% confidence. I was wearing my nerd glasses when it happened. You see, I'm a big nerd. I have a PhD in theoretical physics. I love equations, weirdly enough. I love models, and I love simulation. And OSP had all these good, juicy nerd bits to offer me. But it didn't take long to realize that there was more to it than that. There's a vision behind OSP, that it's much greater and much more important than any of the juicy nerd bits could ever be. As humans, we are always looking to push the boundaries. We continuously strive to invent new things and reimagine old ones. But this comes at a great cost. Because as we move the frontier of what we know and do, the problems that are looking at us become more complex and more complicated. And complex and complicated problems necessitate complex and well-engineered solutions. So the stuff we build has ever more software. I see Armin looking very confused about this AI-generated chip image. He's probably not the only one. But so the stuff we build has ever more software. Things are ever more interconnected, and changes happen faster and faster. And this also forces us to shift our focus from an individual component-centric perspective to holistic full system thinking. Now all of this means two things. We need to collaborate because no single organization, group, or even nerd can grasp the entire picture or has all the answers. And it also means that we need the right tools to be able to streamline and synchronize our efforts and to have a chance at accurately describing full system behavior by modeling, simulating, and testing it. So this collective drive to find the right solutions for the maritime industry in face of this complexity and increasing uncertainty, that to me is the vision. Of course, now the clicker doesn't work. The vision behind OSP. There should have come an OSP slide now. Anyway, that is the vision to me behind OSP. And that is why I found my place as a happy nerd trying to make the future just a tiny bit better.
So I got the controller when nothing works. So it's good. Thank you very much, Severin.
Yeah, no, we were told to blame me, but okay, fair enough.
Okay. I just hope it starts to work. But thank you, everybody, for coming here. I'm very glad that so many of you had the chance to join this event. And I hope that we are about to start a nice tradition and that we can grow this community with people that are eager in solving this co-simulation issue and possibilities. I was about to tell you something about SINTEF, which is the company that both me and Severin represent. Since that slide is not starting, I can say something about myself, that I have a background from the maritime industry, and I didn't start out as a simulation lover, but I love making vessels that are environmental friendly, and I have realized my background is hull designer or ship hydrodynamicist, and I realized that even if I thought so the first years, it's not sufficient to make a great ship. It is the link between disciplines and the big picture and all the small bricks in the puzzle that in total can make a big difference, where you can get large percentages. In order to do so, you need to have somewhere to communicate. And that is not so easy, because to a hydrodynamicist, an electrician, for instance, talk the language of magic. It's not easy to understand each other, but having a simulation like the Open Simulation, or a platform like the Open Simulation platform, make it possible to communicate across disciplines. So then I understood that in order to make a good and optimal vessel, you need simulations and you need good models, and that was my way into models and into simulations. Yeah? Okay. I can try to talk a bit more without slides. Normally I always stand like this when I present, so now this was my punishment. I can say that SINTEF, for those of you that do not know us, we are one of the biggest independent research institutes in Europe, and we are also a not-for-profit institution. And that also gives us, and we have a vision that says technology for a better society. And that gives us some important roles in society. It gives us a role of communicating and providing independent research and innovation. It also gives us a role of providing laboratories and to make software and commercialization possible. And that means that if you take those roles and link them towards the open simulation platform, it is a really good match, because the open simulation platform could be an excellent place of doing innovation and development, testing products and solutions in a safe environment. And it can also be seen as a virtual laboratory, really. And finally, it is a great place for commercialization of products and solutions. In case this will not be fixed, I can just say something about a more like unofficial dream that I have myself. I made a quite bad PowerPoint illustration of how I could wish this simulation platform worked. And that is that next year, instead of showing a PowerPoint of how a co-simulation works, I would love to be the one that actually did it, because that would be a quite good test. If I'm capable of doing it, I'm not on the nerd level of Severin, but I have done some simulations over time, and I think as a former ship designer, I know something about how the systems work together. That is possible for me to do it in a graphical environment, and to drag and drop boxes, and to put these simulations together, and to choose the right fidelity level to match the objective of the simulations I'm doing. And the reason why I say this is that if you manage this, that is when we have done make it possible to have overall everyday engineering tool. So now I can speed through this. I have already said this. And here are our roles, and I think I remember them almost perfectly. And I would also say that, as Knut Tore said, it's quite special location. We are in the middle of a big maritime cluster in a very remote area. But the special thing here is that you can find the entire value chain in a very small area. You can find ship owners, shipyards, ship designers, and advanced equipment suppliers of both local brands and large international brands in this very limited area. And in order to be a part of a cluster, you must be present, because projects in a cluster, they are not generated in teams and in the office. They are generated on the shop, on the football field, everywhere, because everybody is working with maritime things. So a lot of projects that we are working on today is people you meet in perhaps a party or something, and they say, you work with some research things. Have you done anything on simulations? And I can perhaps answer yes, and then okay, contact you on Monday, and then something is starting. This is the thing about a maritime cluster. And that is why also, even if SINTEF is a big company, we have also decided to be located here with 17 regional researchers sitting in this building, and of course standing on the shoulders of more than 2,000 employees in the rest of SINTEF. And that is also why I think that this is a very nice place to gather for the discussions that we will have today. And I hope that, as I said earlier, that this can be a good place to be to solve the challenges and come further. So I didn't find this AI picture that Severin made. So this is the other end of the scale. But it's just a statement that we need to make this platform available for all the stakeholders. And it should be in place as early as possible to follow the ship through the process when the equipment is to be decided, when the shipyard is going to build it for the commissioning phase, and even for the ship owner, so you can make sure that you realize the potential of the solutions. There are a lot of vessels sailing today with advanced solutions that are not utilized. And then, if you're able to then feed this back to the designer so that you can have more accurate simulations in the start phase, then this would really make a difference. So this was this bad slide where I tried to make like a simulation in PowerPoint. But my dream is that I can start with very, very easy boxes for each topic. It doesn't need to even represent the actual vessel. It must just have the basic characteristics and make sure that you have the couplings. And then when you're ready and know some more, you can start with some low fidelity. Perhaps it's not even simulations, it's just links that gives you sufficient information. And then you can gradually increase the fidelity level, of course, to the perfect simulation model of every topic. But normally, this hybrid thing is where you want to be. And that is where we have made, you sit as like a top architect and decide what objective you have. Perhaps here it can be energy and fuel. And then perhaps you don't need an advanced model of the tank. You always need an advanced model of the ship, of course. Since I'm a hydrodynamicist, I would not accept anything else. And then you need lower fidelity for the system and something for the engine. That would be very nice if I next year could have done this not in PowerPoint but in a real simulation environment. Of course, you have this X in the loop thing also, where a lot of the equipment suppliers, I would guess, would be very happy to have a more available tool to test your real components and combine them with a simulated ship, for instance. And then you can, of course, do, this is the top level of the presentation. Then you can do, of course, stress testing and challenge your system, and okay, it's even more, and manage them and get rid of them. No applause, okay. But, So, if I should not look so stupid next year, then I would like to show a real video of a real simulation, so that's motivation. And back to SINTEF again, what we hope to provide in such context is to continue together with research institutions and with NTNU and with industry partners to do research and development of models, contribute to the framework itself, of course, participate in solving the technical co-simulation challenges and facilitate cooperation like we do today. And as I've just been talking about, try to close the gap between research and industry and make sure that we can have this as an everyday engineering tool. And then it requires that someone dares to do the development of the front end and easy to use solutions. And also, we should not underestimate to automate processes in model making and simulation setup, so that it is possible to do it within the time frame, the strict time frame you have when you do product development. So I hope that everybody enjoyed the day, and that we acknowledge that this nerd work in the middle here really can be an enabler for solving the bigger challenges, enabling vessels with higher safety and lower environmental footprint, and that we also really make use of the possibility for networking and just have a good time together, make new relations and new friends, and make a good place for discussing all the important challenges we have in front of us. So good luck with the rest of the day. Thank you.
I was looking the entire day to see when you were doing this. You just stand there, all relaxed, handling the shit, if I may say, out of that difficult situation with the missing slides, so very good. So I expect everybody to have at least 2 questions now. All right, but what actually is the Open Simulation Platform? And question number 2, what's co-simulation? So OSP is an open source industry initiative for the co-simulation of maritime equipment, systems, and entire ship based on the FMI standard. And it aims to provide the maritime industry with key tools and working processes for technical systems engineering. And this enables the efficient and effective construction and maintenance of digital twins for system integration, testing, and verification. But again, then you might ask, sounds awesome, but I still don't know what co-simulation is. And to that I say, excellent point. I had the same realization late yesterday night when I looked over my slides and realized that nobody's mentioning what co-simulation is. So, if you allow me to give you a 60-second crash course into co-simulation, which is the joint simulation of standalone models. Well, that was easy. But why should you care? Well, glad you asked that too. You should care because co-simulation has a host of interesting advantages compared to other simulation types that lend themselves very well for both research and academic use as well as industry use. When you use co-simulation, or when we use co-simulation, we can do our modeling in parallel, and we can use the tools and the methods and the software and the knowledge that we already have and that's best suited to do our modeling. Then we can take those models and we combine them with models from other people, which gives us a very flexible and modular way of creating full system simulations. And it also allows us to reuse models we already have. Another thing that's awesome with co-simulation, it supports black box. And this means is that when you have a model, you can share it with your worst competitor, and they still don't, or they won't be able to figure out what's inside. They can't look inside. It's a black box for all they know, so intellectual property rights are maintained. And the last advantage I'd like to highlight is that co-simulation makes it relatively easy to include hardware in the loop, software in the loop, and human in the loop. Back to OSP. It has 3 key principles. The sharing and reuse of models between organizations without exposing intellectual property rights. It also enables virtual system integration through a standard for model and control systems from any simulation tool or programming language into one single co-simulation. And lastly, cross-organization and cross-platform cooperation through transparency and open source principles. And to get all of this done and adhere to it, there's 3 core components to OSP. So finally, last slide, what is OSP? Here's the answer. It's a C++ co-simulation library called libcosim that is ready to be integrated into any software to give it co-simulation capabilities. It's also a set of demo applications and examples that highlight the use of the library as well as a set of supporting tools. There's the OSP interface specification, which is an emerging standard for how to couple and interface maritime simulation models based on FMI. And there's a set of example model implementations that serve as a starting point for you, as well as inspiration for when you want to make your own models. You can find much more about all of this, plus much more, and in much greater detail at opensimulationplatform.com. Super easy to remember, opensimulationplatform.com. You'll find open software, interface specifications, the reference models, you'll find use cases, you'll find description of projects and much more info there, as well as webinar recordings and recordings from past conferences. opensimulationplatform.com. Obviously, don't go there now, because you still need to be with us and give us your entire attention, because after you've now heard the two personal stories of Christian and me from SINTEF, there's much more to come today, and I very much look forward to it. As Knut Tore said, I have the great honor of guiding you through this day today. We're also going to have a panel debate today, which I very much look forward to. That's after lunch. And for, what was it now, hang out, hang in, hang over, between 4 and 6. It's going to be great. Also, he said outside, not outside, it will be cold, but the outside of the inside. Yeah, we'll tell you later. So definitely join us there for some mingling. Pizza, I think I was promised, yes. And not just me, but everybody. And some beverages. So that's excellent. All right, without further ado, Bjørnavik from Kongsberg will tell us a little bit, maybe a lot, about simulation in Kongsberg. Please, Bjørnar.
Yeah. Almost. I can't say much about this, but yeah, okay. Okay, thank you for having me here. Maybe I can tell my story as well, even though I have the slides already. No, but I'm Bjørnavik. I'm heading a department working with, it's named Cybernetics and Simulation in Kongsberg Maritime. And we're working with cybernetics and simulation. It's a rather generic title. I'll tell a little bit about the different projects we've been involved in, what we in general do in this domain. Touch a bit on OSP as well. Yeah, I think I can just move on. All right. So first and foremost, like Christian and everybody else have been saying, I mean, simulation is important with the ever more complex ships we're building, and simulations are important to KM. This is more on the boring side of a presentation compared to what has been done before here. But so I'm listing up a few of the things. You probably recognize a lot of these themes. But so we use simulation throughout the company and for many different purposes. Probably we can do things a lot better than what we are doing now, but we're doing quite a bit of things. So, for example, simulation-based advisory tools. Now we're towards the operational phase of the life cycle. So these are onboard algorithms that can help us, for example, predict motions and yeah, other things. We're doing a lot of operability analysis, feasibility studies using simulations, even as commercial services. Obviously, early design phase simulations, something we wish to do. Technology qualification, I will talk a little bit about one of the larger projects we've done there within autonomy. Verification, validation, very important. So hardware and loop testing, software and loop testing, all types of testing. It's very important to us. We make a lot of control systems, and those needs to be tested properly, obviously. Acceptance testing, and then training. Basic simulators, 2 bridge simulators. We have one here at the site. Yeah, and obviously then the incident analysis, troubleshooting. There's probably more things we use simulations for that I didn't talk about. These are the ones I could remember when setting it up. Presentation. Then I like to move a bit back because, I mean, we've been part of OSP since the beginning. And really it started maybe, well, when did it start? I don't really know. But for me, at least, it started in this Biproma project, where actually Severin was a postdoc as well. I estimated maybe 10 years ago. I came in 2015, but I think it started a couple of years before. And based on that, there was a lot of talks between us and DNV and SINTEF and also NTNU that we should do something about collaboration. And this is a day in 2017 when there was an agreement put in DNV Sintef Rolls-Royce at that time. I should mention that. I come from the old Rolls-Royce, became part of Kongsberg in 2019. But this started as a Rolls-Royce initiative and continued throughout the Kongsberg Maritime time. So that was the head of Sintef Ålesund at that time, Henning, and yeah, I guess Hans Petter, you're still here. Yes, you will talk later. Okay, then I went into my archives and found a slide from 2016, actually before this point. So I could say this was not a slide as a motivation to OSP like it says here, but it was a slide as to, you know, the different things we wanted to do with simulation and also in generic automation and simulation and improve our processes. And one of the things was to reuse data and reuse models throughout the system lifecycle. That actually, Christian, you just mentioned that I would like to, you know, look at the whole lifecycle when doing simulations. And some models can be reused, some cannot. But for example, what I just talked about, like verification and training, you can pretty much use the same type of models, but it all depends what you want to do. These are just some examples, more like a brainstorming thing, but you know, that was the original maybe motivation to be able to reuse model more. And that was true internally, but also externally. Like has been said here before, nobody, even we, cannot do everything ourselves, and cooperation is necessary to do at least some projects. Okay, so where do we go from here? I just moved directly to today, from 2017. As was mentioned, we have a software, LibCoSim, where from that one everybody can build their own co-simulation platform. But what we want to do, which has also been said before, we want to be more efficient and with sufficient accuracy and reasonable time frame being able to do even complex simulations. But the runtime environment, which we already have now, so that's not the main challenge, maybe because we already have it. But what is needed now is to build a good toolbox for simulations. So for us, it's about configuration, making, you know, automation that was mentioned previously. We want to make configurators that match our control systems and the systems we want to set up. We need the interfaces, obviously. We have, of course, some already, but this is about having a total toolbox that can make it, you know, easy for us to set up any type of simulation. Obviously, some things will always be new and something you can reuse. And very important, libraries with models and also, at least for us, standardized interfaces for a range of different applications. Automation, orchestration of simulations. And orchestration has to do with, you know, maybe scripting a simulation or maybe doing parallelization and acceleration and all of these things that can make simulations happen faster. Yeah, I had to have a slide on challenges as well. Here's at the bottom part of the spectrum when it comes to the most boring slide, but it's a lot of text, but this is how it ended up. So yes, it's well suited for collaborative simulations, but I don't believe that there's one platform for everything. And that's true for co-simulation. You can use it for a lot of things, but not everything. And I just listed a few examples, maybe kind of obvious, but some very specific simulations are better done with tools made exactly for that, like CFD, short circuit analysis, and, well, to some degree also flexible structures. So we are using specialized software for all of these three. And some simulators, many maybe, do not have support for FMI, which OSP is based on. A lot of systems and simulators have support, but a lot don't. So hopefully that can be a standard for everybody to add to their simulators. And it takes time to set up simulator systems fit for purpose. And one important thing is about model assurance, which I guess the DNV will touch upon and is doing work on now. So it's very important. We need to know the limitations of the models that are used. And also, I mean, as part of that, validation of models, for example, using full-scale data is an opportunity we haven't, used fully yet and should do more about. You always have technical challenges such as tightly coupled system. That co-simulation is not really well suited for that, but we luckily have a research project on that called SECO that we are part of. And yeah, as I said, not all models are reusable, but from project to project maybe, but we need to make sure that we have the right model for the right fidelity level. And good that you were here today, Torstein, because I like this figure. It's from your paper, and Kevin, and lots of others actually in that paper. Because we need to look at, what do we want to do? I already touched upon it. Do you want to work here on the millisecond level? Maybe for that level you have a specialized tool because it's a very specialized application. I mean, you can do co-simulation in that region, you can. But the models tend to be maybe a more very specific. The physics may be quite complex, and yeah, you can make those models. But if there's already a tool doing that for you, then you use that tool instead. And you can see for yourself, in this case, a simulator in that paper was made for this region, and this is a region where we have a lot of simulations as well. It's a real-time region where you connect to a control system and do something. And that's one thing about time scale, and also the complexity of what you want to build. Do you want to spend your time building all of this, or is this one necessary for what you're actually doing and want to simulate? And maybe in the region where you look at a very long time, this model could be sufficient. Okay, then I'm jump quickly or suddenly to the next theme, which is another sort of long-term project we've been part of, and that is what we call the University Technology Center. It came from the Rolls-Royce era, was a Rolls-Royce thing. They had a lot of centers throughout the world in many different domains. We continued that during the Kongsberg area as well, and it started out as more like a hydrodynamic type of cooperation we had with NTNU and Sintef Ocean. But in 2018 we extended to what we called cyber physical systems, which really is more maybe about cybernetics and control. And throughout these years, from 2005 to now, we contributed quite a bit also to development of ShipX and VSIM. And as far as I know, VSIM is now going over to using OSP Core in the next big version, or major version, version 4. So that's a good thing. And we might have had a say there, but it wasn't really a hard discussion, I think. Lately we've been doing a lot of stuff within autonomy, collision avoidance, obviously lots of things happening there, and also other cybernetics domain theory. Not much more to say about that. That's been a cooperation that has been going on for like 17, 18 years. So also like OSP, it's something that is important to us to have these collaborations with research and universities. Okay, finally, I would like to just go through one of the major simulation and verification activities we've had the last year or so. And that's this project called AutoShip, which is a quite large EU project on autonomous vessels, where we have been, me and my team have been doing a lot on simulation and verification side. Okay, just quickly what it is. It's an EU project called AutoShip, Horizon 2020 funded, which had two different use cases. I will talk about this one, the short sea general cargo carrier, And there was also an inland waterways demonstration in Belgium. Just a bit about the project, so you have the background. The big demo we had in May this year took the vessel here from Kristvika, from the fish factory location, all the way up to the Ocean Farm 1. It's a 160 nautical mile round trip, about 13 hours, that we're going to do remote control and autonomous. And the remote control center is actually right next to us here in NMK. And yeah, as you can see, all of you that are known here in this region, the vessel went from Kristiansund and up here, so quite a big distance. This is how the remote operating center in this building looks. This is more like a nice picture with lighting and stuff, and this is actually how it looks, you know, a regular day. So, okay, over to the simulation and verification part. Yeah, I tried to find maybe a simpler picture of the setup, but the whole point of this picture is to tell you that this was quite a complex setup. I can just go quickly through, but we have some sensoring up here. We have what you call situational awareness, detecting objects. We have autonomous navigation system that we need to integrate. M100 is the autopilot and the thruster control. Here on the machinery side, you have the IIS and the PMS included there. Something called digital chief and arms, which are quite, let's say, autonomy layer systems, and then a digital master, which is also autonomy layer system. So all of these three systems here were new, and these were not old, but mature products. And then we had a connectivity solution. So this is communication between the vessel and the remote operating station workstations. So rows for navigation and a rows for engineering, which had then, you know, remote versions of all the systems, and then some extra systems that you can see here. This is the visualized version of this proximity view, which is actually a camera system telling you what is around the vessel, even with overlays of objects. Yeah, and also radar and ECDIS and all of these normal things you have on a vessel. So basically we had to simulate everything you needed to make this work. So, and the total setup you see here, I mean, we used it for crew training. So then we had a gang, not a gang, but a part of the crew, one set of crew in the rock, and then another shift in the simulator dome, which is also here, and these were connected through the same connectivity system, and we could do crew training. So this would then represent the vessel. And when doing that and going over to real sea trials, we could just switch to, well, actually I think I have it here. That we then connect the rock to the actual vessel. And then when we actually continued doing simulations throughout this period, when we were on board, this was a research project, not everything was 100% correct when we took it on board the vessel. So then we could then quickly go back and test things in the simulator, actually with things, bugs we found on board, and that being fixed, and then simulator, and then vessel again. Actually, this was quite a fast cycle of working. So, yeah, okay, yeah. Maybe didn't need to include this, but as part of this was not only simulation, but visualization. So the whole route visualized the vessel, and the Ocean Farm 1 was visualized, even a bit of Kristiansund. And that is something you needed to incorporate in the simulation as well. We needed to produce images and radar images and everything that you needed to set up this rock in a simulated setting. Okay. Then last slide. Basically a conclusion of what we did. I already said it. we did a staged approach, doing first sort of just control part, and then we extended to having a connectivity system and also the rock after that. And crew training, human factors activities as well during crew training, very important. And we, crew training is important also because we got a lot of good feedback from the crew to the behavior of the autonomous navigation system and the whole system setup. So yeah, and we did it also in several iterations, obviously, as you normally do with software testing, even after the vessel was sailing. So we had maybe 9 sea trials in total, including the actual demo. So really a good period that found a lot of... I have to say that some things came up on the vessel that we didn't see in simulation, because simulation is not perfect. But again, a lot of things was found in simulation. And that takes me back to sort of the conclusion here that yes, we set up this system. We had a large research project to do this, but we should have done it much more efficiently. We used sort of co-simulation, we could say, but not fully OSP. So there's a lot of potential for setting up stuff like this, because you can't do this for a lot of different projects. But yeah, in research you can do it. Yeah, I think that's it for me. Thank you.
Thank you, Bjørnar. One important thing I forgot to mention, maybe first and foremost to you. Hold on. Yes. There's going to be a chance for questions and comments. Oh. So don't take that mic off quite yet. We are... Yeah, well, you actually finished on the second, yes, including my babbling now. But I would like to allow for, let's say, 2-3 questions and comments. Who does the mic audience? I can do that otherwise. Who has a question? And what question do you have? Don't be shy. Yeah, very good.
Hi, Bjørnar. This is Goyan from NTU. So regarding this remote operation center, so I see it's a purely research perspective. So what do you think, how long will it become too true for use? What's the challenges and gap from the research to real application? Thanks.
This is a research project, but we already have a company set up together with Willems, I think, called Masterly. Those will be responsible for the commercial operations. And as far as I know, it's already, if not in operation, then I think it's close to being in operation with the ASCO and Yara vessels. I don't actually have the latest here, but it's all being set up for that. So, yeah, I didn't say too much about the results in this project, but I can say that we sailed for 13 hours, where the crew on board took over once due to some things they saw in some buoy or something that wasn't detected. And I think there was a glitch in the communications as well. But other than that, they did full autonomy or remote controls. I think, having remote control is not that, far ahead. It's more about, I guess, regulations and stuff like that. But I don't have a full info on that, I would say.
Don't look at me. I want to unleash all the technology onto the world. Thank you. Another question or comment? Yeah? Let's see. Yeah, I'll save that for later, maybe after I had a beer and aim better, which of course I'm not going to have at this time of day, just in case that was not clear. That wasn't clear.
Yeah. I was wondering, you both have remote control and also simulation. Is it possible that you can actually do a simulation and remote operation, remote control at the same time? So you're actually updating your model with real-time data from the vessel, or are you switching to either doing remote control or doing simulation, or do you have some hybrid way of dealing with this, or?
No hybrid way now. It has to do with the safety as well. But yeah, I was had a point there on validation of models, and this is something that, of course, is important. But we're not utilizing simulations in operations in any way right now. But obviously, it could be, support systems, advisory systems on board, but not really connected to remote control. No. I don't know if I understood the question correctly, but no.
If I may be so bold as to finish with a question of my own, which I hope is relevant for a lot of people. Even though you love to sell yourself short, it's evident that Kongsberg has gotten pretty far on this journey. But there's only one Kongsberg, and
Which
most
journey?
of us... Huh?
Which journey? The OSP one or the autonomy one?
I gave you the entire speech about the OSP vision, so
okay.
that journey. No, but you've come very far here, obviously, and you also have the strength and the resources to do that. My question is, what advice do you have for companies which are at the start of that journey, who maybe haven't even yet taken the first step, or maybe they have taken a few first steps, and or companies that don't have the muscles that Kongsberg have? What advice would you give them if they want to do similar things?
Okay, that's a difficult one, but I mean, basically you have to look at what problem you want to solve, and then you need to find, the right tool. If that is code simulation, I guess that's what you want it to be. Or if you want to use some kind of commercial application, I mean, there are now commercial, providers of code simulation platforms, so you could use another tool that supports FMI, and you maybe can use that as well. But first and foremost, like I said before, it's about finding the right tool for your problem. And it might be OSP, might not.
Might not, no?
Sorry, not the right answer maybe, but...
No, I'm a nerd. As long as it has equations, I'm good. All right, thank you very much, Bjørnar. Next up is Tim Mak from Vard, who will also tell us a little bit about Vard's perspective with simulation.
Okay, now we're good. Okay, I guess shortly on myself, I guess my background is also hydrodynamics. When did I start using OSP? I think I was also involved with a project called Vista Project, which was going the same time as Viproma. And I think 17's been quite modest here when he says he doesn't recognise the start of OSP, because I think he's really one of the fathers of OSP, because and with you, Severin, yeah, because you were involved in writing the Coral together with Lars, so and I see that as the predecessor of OSP. So, yeah, so he was right. I was just pointing out. You were doing the maths, so. Yeah. Anyway, so how's this work? Yeah, I've tried to keep the corporate part down to a minimum, but for those that are not aware of Vard, we are Fincantieri's expert in offshore and specialised vessels. Our headquarters in Ålesund. We have 7 yards, 3 locally, 2 in Romania, 1 in Vietnam and 1 in Brazil. Roughly 7,000 employees, and order book from about a year ago says I think still got 30 odd vessels on our order, and delivered over 400 vessels since 2000. We're involved in the design from the concept phase and right through to obviously building the vessels and integrating all of the parts and supplying lifecycle services through maintenance and classing throughout the vessel's lifetime. How do we use simulation in Vard today? So I know that Vard Electro are doing a lot of PMS testing. They're also doing short circuit analysis. They're using MATLAB Simulink a lot. At Vard Design, we're doing a lot of CFD optimization for our hull forms. We're just commissioning a new HPC cluster at the moment. We're also doing ship motion analysis, station keeping analysis, DP analysis in-house, and I'm also using AIMSIM for system simulations, which is a great tool, but which also supports FMU, but you're also locked into that environment. So when we want to incorporate other simulations from outside, then maybe it's not the best environment. So that's where I think OSP has a role to play. Psionics, we were providing cranes and gangways. They're also building their own training simulators for crane operators as well. But we still have to be honest and say that the communications here, simulation-wise, are not could be improved. Recently, we did a project in the Offshore Simulation Centre up just behind us, together with RemPower, OSC and DigiCat. We were trying to simulate the operation. Offshore Ocean Charging Project is about how to connect to a offshore charging platform offshore so that you can recharge your battery-powered vessel. So we tried to simulate the operation in the OSC. And that went pretty well, I think. We used the actual crane operator and the skipper from REM we went through the operation, and we were able to get the crane to hook up to the charging cable in the sea states we're interested in. So it looks promising, I'd say. And we're going to do the full-scale operation in March of next year out at the Zephyrus test platform, which is the floating offshore wind turbine you see here in the background. So, how do we use OSP today? And yeah, we have some challenges with that. And to be honest, we have used OSP very little. I think part of the challenge is that the user threshold to come in, get started, is quite high. And one of the other challenges is the standardized interfaces. Well, the vision for the OSP looks great, and the co-simulation runtime platforms is quite a big improvement over what is originally with Coral. So I think we've come quite a way, but I think we see the same problem as Björnar mentioned, standardized interfaces. They don't really exist at the moment. So if we have a model of a tunnel thruster from one supplier, it doesn't mean it's the same as the interface for another interface from another tunnel thruster provider. So each project you'd have to begin with a discussion about, well, what are the interfaces? And yeah, it doesn't make it easy to get started. So, but we clearly see a need to start using OSP more. And that's why we're going to, with the C0 project, which is a cooperative project together with Hurtigruten and 12 other partners to develop a zero-emission ship sailing along the Norwegian coast, which should be ready to sail by 2030. We're going to start looking at using the Simulation Trust Centre with these 4 partners, TNV, Brunvoll, Sintef and Vard. It's work we've started discussing, and I think we're going to have more discussions tomorrow to really get the ball rolling. So I'm really hopeful that could be a good test case for us to get started on OSP and really get to understand what we can do. And looking forward for the future, we obviously see a need for more use of simulation. I think OSP is obviously still a good platform potentially for cooperation and incorporating other third-party models, or even internally within Vard, we see the need for better interfaces between our simulators for reuse and just better integration, communications between the different companies internally and externally. So, yeah, that's basically all I had. Oh, no, there's one more. I had one idea which I wanted to bring up today, discuss with you people in the audience. But perhaps we could also include the optional of mapping signals used in the OSP simulation to the signals that we use on the ship. For example, if we're using the VIS standard on the ship, why can't we use the same VIS standard in the OSP interface for the components to simplify the comparison of real data with simulated data? So that's just an idea I hope we can discuss later, and perhaps we'll get it into the OSP interface in the future. So that's my short presentations for today. So I'll hand it back to 17.
Awesome. Thank you so much. Again, we're a little bit behind schedule, but and next up is the break. Can we push the next talk after break 5 minutes back, you think? Okay. Then I would say we have some time for questions or comments, or a hybrid of both if you want to get creative. What questions do you have? Everybody put their thinking face on. Siegfried, yeah?
Beyond this VIS standard you mentioned, are there other standards which could be used for this standardized interface between component models?
I guess there's the Japanese interface, Japanese naming standard as well. I'm thinking the ISO, was it 848, which opens up for using, for example, the Japanese standard or VIS.
Mm-hmm.
Yeah.
And that is good enough to do most of the things, or is that only a sub-part of what is needed? I don't know.
Not sure I know the answer either, but I think we can do a lot with this.
Klaas, yes.
Sorry that we're so intensive. No, just one comment to this naming. Say my experience is that it might be a good idea to not merge the responsibility of naming something with the responsibility of identifying something. So because there will always be different naming standards, be it in different industries or with different customers, and I always feel like this wish of an industry to have one common naming standard is one of the hardest challenges to solve, and has maybe never really been solved down to the nitty-gritty details. So, and I'm just thinking maybe we could have something like an abstraction layer in between, so that first of all we would identify any artifact, like an input and output parameter, something with something that has no meaning, say a unique identifier, and then have mapping tables kind of that, say, okay, I use this naming convention, so it maps to that naming convention. That could even, for any visualization and something, could be dynamically displayed. Just as one thought on that.
Yeah, I think we have to talk about it some more.
I mean, there's, not to put you on the spot, there's of course light at the end of the tunnel. There's the next talk after the break now is by FMI, which is the standard for co-simulation, or from, not by FMI, it's by Christian Birch from Siemens, who is the chair, I think, of the FMI group at the moment, and they're working. So the research, like the community and research is aware of this problem. We recognize that it's a big one, so both OSP as well as, of course, FMI are working on this. We'll have a quick follow-up question. Would you say that this is the largest showstopper? Because you said it's difficult to get into and get going.
Yeah,
is that the
I'd say
biggest
that's
problem? Or is there,
yeah, I'd say that's the largest showstopper. Not the naming, but yeah,
no, the interfacing.
just getting started, and the interfaces, like agreeing on having. I think the vision originally for OSP was like have some sort of marine standard interfaces for a thruster, a drive. What is that going to be? And we came down. We got the very generic OSP interface standard, which is forces, currents, and which is obviously
but you need
good
another layer.
start. But then the next layer, how do we standardize what is a thruster or what?
Yeah, exactly. Very good point. Okay, how much time do we have for the break, Knut Tore? I choose. Anything between 1 second and 2 days? 10 minutes as planned, I would say, is good. So then shall we have the next talk starting at, 11:25? And again, that's Christian Birch from Siemens, who talks about FMI, current developments and future outlooks. Very good, thanks for now. Oh, there are...
Yes, I can hear you. Can you hear me? Very good.
Do you hear my microphone as well? Do you hear me now?
I can hear you well, yeah.
You can hear me now?
Yes, I can hear you.
Okay, super. Wir können übrigens Deutsch reden. Ich bin Österreicher. Also nur
The last thing I didn't get here.
Ich sage, wir können Deutsch reden. Ich bin Österreicher übrigens.
Ach so, alles klar, gut.
Ja, aber du hörst mich gut, oder? Weil es ist wichtig, dass
okay.
Jetzt hörst du mich auch noch gut?
Ich höre es gut, ja.
Ja, sehr gut, weil ich habe das Mikrofon, dass ich weiß, dass ich dann nachher, dass du mich hörst, wenn ich mit dem Saal rede und so, dass du ein bisschen Feedback bekommst auch. Wir würden nämlich gerne noch Fragen vom Publikum zulassen, wenn es für dich in Ordnung ist.
Jetzt reden gerade mehrere auf einmal.
Achso, jetzt reden die da drüber.
So, several people were speaking at once, yeah.
Ja.
Okay.
Christian, hörst du mich noch? Nein. Hörst du mich?
Ja, ich
okay.
höre ja.
Entschuldigung, mir ist das mit dem Ton, ich möchte, dass das wirklich passt auch für dich, dass du hörst, was wir sagen und dass du ein bisschen
Alles klar, das passt
Feedback
gut, ja.
vom Saal bekommst. Ja.
Ja.
Christian, wir werden dich auf dem kleinen Notebook hier haben. Wir werden dich umdrehen, sodass du dann die Bühne siehst und dann auch mich. Weil wenn wir eine Fragerunde haben am Ende, dann haben wir da ein bisschen Interaktion. Weil ich schätze mal, wenn du remote bist, du hast sicher viel Erfahrung damit, aber ist immer ein bisschen schwierig, den Saal natürlich mitzubekommen, was da on Location passiert.
Genau, prima, das ist gut, wenn ich dann was sehe.
Ja. Und sehr coolen Pulli übrigens.
So you have not yet started the camera, right? You will do that. Yeah, okay.
Da arbeiten wir gerade dran. Ja.
Yeah, okay.
Alles nicht so leicht mit der Technik.
Now I
Jetzt.
see Ole, yeah. Oh, who?
Ja, danke jedenfalls nochmal, dass du Zeit hattest auch. Das ist natürlich eine gute Bereicherung für die Open Simulation Plattform Konferenz, dass wir da von der, wie heißt es auf Deutsch, von der, ja auf jeden Fall von FMI und von dir da Einblicke bekommen. Das ist ja sehr zentral natürlich.
Gerne.
Vor allem das mit den Layered Standards. Also wir haben gerade die Präsentation vor dir, war von Vard, also Industrie, im Maritimbereich hier, und die haben gemeint, einer der Hauptprobleme, dass man Co-Simulation anwenden in der Industrie, ist, dass die Interfaces zwischen den Modellen nicht gescheit definiert sind. Also so quasi fürs Maritime zum Beispiel, du bräuchtest eigentlich eine gute Definition von einem Propulsionsmodell zum Beispiel, wie das Interface aussieht. Und das ist natürlich dann die Frage, die zumindest ich jetzt habe, ist, inwiefern die Layered Standards da das komplementieren können, dass du quasi diesen Layer oder diese mehrere Layer vielleicht on top of FMI machen kannst.
Ich könnte sehr gut passen, ja.
Ja. Jetzt siehst du auch mich.
No.
Christian, wir werden die Leute jetzt in den Saal bitten. Das heißt, es geht dann bald los.
Alles klar.
All right, welcome back, everybody. Hope everybody's refreshed and had their coffees. Next up, something I am very much looking forward to, because the key enabling technology in all of this is FMI, the FMI standard, which emerged from the car industry. And with us today, remotely from Germany, I'm guessing, or where are you at right now, Christian?
Yes, south of Germany,
Yeah.
Stuttgart.
Yeah, very nice. Is Christian Bertsch from Bosch? I said Siemens earlier. I'm very sorry for that. That was completely wrong. Please take no offense. I come in good faith. And you're going to tell us a little bit, or maybe a lot, hopefully, about the functional mockup interface with a twist on new features in the newest version 3, and as well as extensions with layered standards. So please, Christian, floor is yours.
Thank you very much for the nice introduction. So, very briefly about myself, I studied mathematics and physics and work at Bosch since 2001, now at corporate research there. And for about 10 years, I also represent Bosch in the FMI project, in the steering committee, and since last year, I lead that project. So the outline of my talk is as follows. I will briefly summarize the basic idea of FMI, and then talk about new features in FMI 3.0, which is the latest major release, and then talk about extension mechanisms in so-called layered standards. So these 3 parts are based on separate talks, which I also have put here as links. I will later provide you also the slides, so there you can, for each of these topics, also go into more detail. And then I plan also to have time for questions and answers session. So plan is for these first 3 topics to talk about 10 minutes each. Okay, the basic motivation behind FMI is to develop a tool-independent standard for the exchange and co-simulation of models, and to provide them in a containerized form so that you can also deploy them to different targets, and by this also decoupling the know-how between producers and users of models. And this enables the massive reuse of models in different environments and also in some form IP protection. So FMI was developed in a large European-funded research project, so-called Modellisar project. And after it was developed, development was continued in the Modelica Association. So Modelica is a modeling language for especially physical models. But technically, FMI is not related to Modelica or not limited to Modelica. There are some historical connections because, let's say, all the tool vendors that support Modelica, most of them also contributed also in the development of the FMI standard. But as I said, technically, FMI is not limited to Modelica, but it's now the home of our project, this Modelica Association. And FMI was developed, I think, quite fast in this research project, FMI 1 and 2. Then we had some time of adoption, and then now came a big step with FMI 3 for new features, which I will also comment on. So regarding this versioning, I will explain the numbers. So if you see FMI 2.0.4, so FMI 2 is the major release. This brings really new features. If you would have a FMI 2.1, there could be new features in a backwards compatible way. So there was no 2.1, but we aim for a 3.1. So the idea is that a 3.0 FMU is still a valid 3.1 FMU, but FMI 3.1 FMUs can have new features. And then there is this last digit, which refers to maintenance and bug fix releases, that are for clarification, for example. Okay, So FMI is an interface description that is more or less a contract between the exporting tool and the importing tool. So you develop a model in some tool, then you export it in a form of a so-called functional mockup unit according to the standard, and then you can import it to some other tool. And there you can simulate or co-simulate it. So the scope of models, this was originally mainly, let's say, physics-based models that you can describe with ordinary differential equations that you solve with some numerical solver. But now it's also used beyond that, so it can also be purely algebraic. We also in FMI3 introduce more discrete behavior, and also it's very broadly used, for example, for electronic control units or now AI models, so it's not limited to the classical ordinary differential equation-based models. The FMI standard describes the interface, and especially it consists of the description of a C API. So you have some binary code, and the standard explains which access functions you have there. And it describes a schema for a model description XML file. And it describes how to organize the exchangeable unit. That is this functional mockup unit. So this is a zip file with some internal structure. So there are defined directories and files inside this zip file. What's very important, the FMI standard describes only the interface. So it more or less the model itself is some kind of black box. And also the co-simulation algorithm that you need to simulate multiple FMUs, or the solver that you might need for a model exchange FMU, which we'll see in some time, this is not defined by the FMI standard. So as I mentioned, this functional mockup unit is a zip file, and you besides this schema, this model description file, according to the schema, you need at least one model representation, typically in binary form. So for Windows, this would be a DLL, for Linux, an SO file. Or it can also be a source code, so that you could recompile it to some new target. And you can also put several binaries for different platforms into one FMU. And there are additional folders defined where you can put additional resources, could be some data, documentation, icons, and so on. And what is new is the extra directory that is reserved for layered standards, which will be the third part of my talk. There are, in FMI2, there are two kinds of FMUs. So-called model exchange FMUs or co-simulation FMUs. For models that are based on differential equations, the main difference is whether the solver for these equations is inside the FMU or whether it comes from the importing tool. And there are certain pros and cons. So here with model exchange, you have a very tight integration of the model in the simulation tool where you import it. And this is also reflected. The API is much more complicated. So, for example, you more or less you have all the functions how the solver interacts with the model. In industry, mostly co-simulation FMUs are used because here the interface is more lightweight. You have fewer access functions that you use, and also you can make sure that the model and the solver, they fit together. So for example, if you have very stiff hydraulics, you know that you have a fitting solver for that. On the other hand, as in the code simulation, you communicate only at discrete communication points. There is still, you make some numerical error, and there's still a freedom how to select the time step for the communication and to select the suitable co-simulation algorithm. Model exchange, for example, is more used. So some tools use it as their native form of integrated models. So, for example, from Modelone, they have FMI as native format, and you can also interface the Modelica compiler by a company Modelone, for example, in AIMSIM, and in the background, they do this with this tight integration of the model exchange interface. In co-simulation, more or less, the basic sequence is you set values, you make a do step that advances time and triggers the calculation, and then you get values. And as mentioned, the co-simulation algorithms that might do some interpolation or so, this is not defined by the FMI standard, but it's a freedom of the importing tools. I also mentioned this model exchange. We have this tight integration with a more complicated interface. I will not go here into details. And also this I mentioned, so we are not limited to one FMU. You can, I think OSP is one example where you can integrate multiple FMUs and do some co-simulation. And here you can also select, for example, the time steps and this suitable co-simulation algorithm. Here with a model description, you define the interface, which variables are there, inputs, outputs, and so on, parameters. And there is also a variant for co-simulation where you need an installed tool, and the FMU that you get is only some, let's say, some dummy which communicates with the installed tool. There are some use cases, but on the other hand, this is not so good to use because you still need this simulation tool installed on the target machine. There are many tools supporting FMI. I would say all tools on the system level today supported in some way. It's more than 190, and also some tools, for example, in the finite element or CFD field supported, and also tools that are used to create embedded software supported. So it's really a very long list, which still grows very fast. And also there are interfaces to many programming languages, so whatever C, Java, Python, Rust, whatever. So there are libraries to run FMUs. The most up-to-date list is on the FMI webpage where you can access and search for tools. There's a latest development that in this tools list, we also have the possibility that the tools describe how they tested their FMI support. So importing tools report which FMUs from other tools they have simulated successfully, and exporting tools provide example FMUs and say with which importing tools they have tested. So this is very much recommended, so that tool vendors provide this information, and then they get this a golden star and a link to this to a repository or web page where they document this. It might be that FMUs contain licensing mechanisms in a technical form, so that you need FlexLM, for example. This is not limited by the standard, and as there might also be other obligations that you have to follow with generated code in principle, also as in other cases. This is not described by the FMI standard, but you can put such information also inside the FMU. Okay, that was FMI 1 and 2, and let's see what is new in FMI 3. So FMI 1 and 2 was very successful, and I think part of its success was also the stability, that we did not have big releases every year, so the tool vendors could concentrate on the implementation. But now, over the years, in some fields, new needs came up. So, for example, in the field of the more discrete world, like virtual control units, also needs for advanced co-simulation schemes, also in larger systems, especially with discrete events, one had to see how to synchronize events, and also new fields like AI applications. And this triggered the development of FMI 3, where besides the two kinds of FMUs that we saw in FMI 2, this model exchange and co-simulation, there is a third kind. This is special for certain, especially real-time control software tasks where you can externalize the scheduler. But this is also not yet broadly supported yet by tools. I will not comment further on this scheduled execution because it's a quite special use case. But even in the other fields, there are very important improvements. So in the past, in co-simulation, we had this discrete communication points. Now there is also an event mode. You can, as an example, you simulate in the FMU to detect that some discontinuous change happens. I will have an example on one of the next slides. There's there's a possibility to communicate values between the communication points, to synchronize events with clocks and define discrete systems, to more in more refined way defined variable types. Also, the possibility to define array variables within FMI2 was only possible with a naming convention, but in the background, this was still scalar variables, terminals and icons. This is about better API possibilities. So, for example, you can have physical connectors or something like a bus where you group many signals. And I mentioned the scheduled execution and also these layered standards, which will be the third part of my talk. I mentioned these data types. So in FMI 1 and 2, you had, for example, for integer only one type. But if you define, for example, an electronic control unit and want to simulate it more accurately, then it's now better to really define the concrete data types. There's also a new binary variable, which is very interesting, especially also in the field of layered standards, because you can then define a MIME type, declaring what is communicated with this binary variable. And it could be, for example, camera data or some format defined by someone else or in a layered standard, and you can just communicate it in form of this binary data, and a clocks type that is needed for this discrete behavior. The array variables was mentioned. So this is, I think, for large data sets, much more efficient. So this is a good improvement. Similarly for the terminals and icons, which is, let's say, this is not really for the functionality. This is more for the how do you display it in the GUI. So you can define physical ports where several inputs and outputs belong together, and then you can connect them just with one line, just as you would do, for example, in a Modelica tool. And I mentioned this discrete behavior. So one example would be a bouncing ball with FMI2. If you do a co-simulation or have a co-simulation FMU, then you have discrete time steps. And when you miss the time, as displayed above, where the ball hits the ground, there is no way to get information out at the time. But with FMI3, you can say now that the FMU detects this time when it hits the ground. And even though a larger time step in the do step was intended, you can trigger an early return. So the FMU tells the importing tool something has happened in a discrete event, and then at this time information can be exchanged. Also, it's possible with intermediate update to exchange information even between the normal communication points. So this is more for, let's say, continuous behavior and also for advanced co-simulation schemes. It's possible to exchange information, but it could also be used only for display. So currently in a co-simulation FMU, you can have internally a variable time step solver and do larger, for example, fixed step communication time steps. There is no way currently of getting information out. But with this intermediate variable access, you could, let's say, bring internal solver steps. You can output variables. And you can use this also for advanced co-simulation schemes. For example, doing some extrapolation in the co-simulation algorithm, and then also at the intermediate point providing higher order interpolated variables. the clocks I mentioned. This is more for discrete behavior. There are several types of clocks, so more for, let's say, fixed time steps, but also triggered clocks. So there's a lot of possibilities. Overall, the clocks are used to synchronize events or synchronize the discrete behavior between multiple FMUs. So I think this is very powerful. Yeah, here are also listed these different clock types. So it's really very powerful. One has to say that the implementation of all these FMI3 features, this will be step by step. So not all the tools that start implementing FMI3 will, for example, support all these capabilities of the clocks type at the first time. But yeah, I think in the future, this really enables lots of use cases. For AI applications, also in the past in FMI2, it was possible to get partial derivatives in the form of directional derivatives. But if you have, for example, a neural network that you encapsulate as an FMU and you want to further train it efficiently, you do typically backpropagation, and there you need not the directional derivatives, but more the adjoint formulation of it. And this is also now enabled in the interface. So you can also in the future have AI applications where you, even though the model itself is black box, from the interface, it's supported to get these adjoint derivatives that you can use for efficient further training of such models. Okay, so now coming to extensions. So in the design of the FMI standard, it's always the question how general we have the standards, or how we tailor it for specific use cases. And one of the design principles is to keep the standard very simple, but on the other hand, allow broad application. And this led to the concept of layered standards. So more or less the idea is to keep the core standard simple and general. And if you have more specific use cases, then define it in other standards on top of the FMI standard. And this idea was first introduced in the Modelica Association standards in the SSP project, that stands for System, Structure, and Parameterization. And we in the FMI project, we took over this idea. So yeah, we have now this idea, as I mentioned, to have a core standard which can be extended in layered standards. And these extensions can be by different parties. So it can be by anyone. So for example, one company, so Bosch could define a layered standard for certain use cases, or a certain industry like the maritime industry could say, we define, for example, we agree on certain connections of models in form of these terminals, so that, let's say, if you exchange models between these different companies, these models fit together. And it's possible that also if there are, let's say, very broadly used or good standards, that also the Modelica Association project FMI endorses such layered standards, or we from the FMI project, we on our own could also develop layered standards. And I will in the next slides, I will present some examples of such layered standards that we are currently working on. So this is introduced in FMI3, but also this concept was backported also to FMI 2.0.4. Here we did not fully follow the principle that in a maintenance release, you do not introduce new features, but here this is nothing that changes the core functionality of the FMI standard. That was the reason why we here, let's say, introduced this concept also to FMI 2. And the following three examples we are currently working on in the FMI project. There will be a layered standard for XCP support. So I will have a slide on that in the next slide. So this is a standard for the measurement and calibration, or especially in the automotive field. The biggest thing that we are currently working with is a layered standard for network communication. And then there is also the idea to structure variables and also enable maps and curves and some smaller other ideas. So these layered standards can be realized because the core standard already has some extension points. So I mentioned this extra folder, and by a certain naming convention, layered standards can put in a certain subfolder of this extra directory, they can put additional information. Also the XML, this model description XML, this can be extended in a standardized way via annotations. One can define new terminal kinds and matching rules for these terminals and icons. And also, it's in principle possible to add new API functions, even though this might perhaps not be a good idea because name clashes could occur here. And there's also a way to announce that an FMU supports certain layered standards in form that, let's say, in this corresponding subfolder, a certain manifest is put, so that in the future also an importing tool, when it gets an FMU, it can also display to the user, this FMU supports the following layered standards, so that the user gets this information in a standardized way. This layered standard for XCP support, it might be automotive specific. I'm not so sure. So it's a protocol that you can, from an electronic control unit, you can read out data and also set values in the measurement and calibration process. So this is quite advanced. There also it contains different ways with XCP server internal or external. I will not go here into details. Good thing is that this is almost ready. So there's a release candidate out, and currently we are just waiting for prototype implementations, because before we release a standard, we always want that the features get tested in prototype implementations, and this is the status, the state where we're currently in. The standard itself is ready. This layered standards for network communication, this is really a big thing. So in the past, FMI2 was first mainly used for continuous systems. This was also, let's say, where the design came from. But now more and more, for example, in the field, in the automotive industry, it gets used also for simulating of bus communication, virtual ECUs. But here, this was not covered by the core standard, and now let's say there are incompatible versions out by certain companies or tool vendors. And now here for this layered standard, we wanted to make use of the FMI3 mechanisms, for example, to base on a co-simulation FMU together with clocks to describe the discrete behavior, and also certain terminals where you can group the signals, and also the definition of certain binary variables where you communicate the payload. And the idea is to more or less that this can be used for any kind of network protocols. So currently, this was from the members of this group, it's automotive focused, but from the standard itself, it's not. So we currently, CAN is already described as that's the most common bus protocol in the automotive industry, but also for LIN, FlexRay, CAN, Ethernet, let's say more or less we know how we would do it, and this will follow fast. But it would be very interesting to get feedback from other industries. So I don't know in the maritime or industry if there are other kind of buses, or whether you also use some of these buses that are used in the automotive field. Perhaps later in the discussion we can elaborate on that. So here, as we base on the FMI standard only, we get rid of certain side channels that were used in this proprietary solution. So in the future, if you have such an FMU that supports this standard, you can, let's say, communicate only via the standardized FMI interfaces according to this layered standard. And then if you have more detailed bus effects like arbitration, either the importer does it, or you can also define can also define an FMU that that simulates this special bus behavior. And there are currently two abstraction layers, the high cut and the low cut. The high cut is more on the signal level. And the low cut, this is on the so-called microprocessor abstraction layer. So this is perhaps automotive specific, but here you more or less are closer to the hardware and simulate more detailed effects. This is already also quite advanced. So we will have a release candidate for the CAN support soon, and for others, for Ethernet and LIN, we plan at the same time with the 1.0 release to release an alpha where we already sketch how this can look like for other networks. And as mentioned, feedback from other industries is very welcome. The third layered standards that we work on is for grouping of variables and regular maps. So we now have arrays in FMI3, but currently you cannot describe, for example, a map on a regular grid. Here you would have to define what are the domains and then codomains and what is the data. And here we currently work on a description where we use the terminals concept, how to describe such a map. So this is not such a big thing like the bus simulation. I think the ideas we have discussed, we just have to write it down and then release it. There's also some smaller standards in work. So the idea is to store, for example, a reference solution for an FMU together with stimuli, so that you can do a first test of this FMU. Also, idea is to store the source files from which the FMU was created. So, for example, a Simulink model or a Modelica file you can store inside the FMU, or several parameter sets. And this could be according to the SSP standards. So you could put several SSV files into the FMU so that you can later select, for example, for one electrical machine, you could select between several parameter sets that describe several variants of this machine. Okay, so this was, I think, lots of information, but there is more. So you can go to the website, go to the tools list, and there's also some tools for the validation of FMUs. We have a list of publications. There are the reference FMUs that is perhaps more interesting for implementers to test them. You can discuss questions on FMI. So we recommend their Stack Overflow that you tag questions with FMI, and there's also a LinkedIn group. That was all from my side. So I'm open for questions.
Thank you very much, Christian. You might not be hearing it, but people are clapping for you for sure. All right.
It was not very well audible, so.
Oh, sorry. No, I just said you might have not heard it, but people were clapping for you. Yeah, my microphone.
Okay,
was not,
thank you.
That was, I guess, the problem. Thank you very much. I wrote down like 20 questions, but I'll try to hold back. Questions, comments for Christian, who wants to go first? Thomas has a question from Kongsberg. I'm gonna jog up to him and give him the microphone. Meet halfway, yeah.
I think one of the benefits of FMI 2.0 was that it was for co-simulation, that is, because that's the one I am familiar with, is that you can almost ignore most of the API. There is just a few functions you need to implement to actually make a very bare bones FMU. In FMI 3.0, you have added lots of new functionality to the interface. So how has this minimum set of functions that you need to implement increased from 2.0 to 3.0?
So I think you can do everything that you can do with FMI2, you can also do with FMI3. And this is also what tool vendors will do in the future. So here one must perhaps distinguish the standard itself, that it describes lots of things. Some of them are optional. So, for example, this event mode that I mentioned in co-simulation, this can be indicated by a capability flag. So this is not in this minimal set. The minimal set has changed in this form that you have these new data types for which we have new access functions. So I think these should be implemented all, but yeah, and also the new types like arrays and binary, I think they should be supported. Then there are several optional features, but we are also aware that on the one hand, not all tool vendors will support all FMI3 functions at one time, and also, especially also not these optional ones. So we plan to make this also more visible. So in this tool list that I mentioned on the FMI webpage, we plan in the future also that you can that tools can also, especially for the optional features, then display which of them they support, so that you could also more easily filter, for example, which tools support this event mode in co-simulation or so on.
Great. Another question? Otherwise, I'd like to be a little bit mean and challenge DNV if they would maybe like to say something about the model assurance they're doing and to what extent FMI is well aware of and interested in that. Siegfried?
Yeah, I don't know whether you have heard about that, but in DNV we have developed assurance of simulation models, recommended practice. With what you say, it seems to me that this is probably one of these layered standards where we could say, okay, this FMI also supports these assurance features. Maybe we should arrange a meeting at some point in time also together with Klaus, which sits at my side here. It has also been part of the development, because I think it would be interesting for some FMI models to support that, because when things get critical, we need trust in the models, and that is what our RP is heading towards. It's only out as a first version, and there is room for improvement. Maybe you have also ideas for that.
Yeah, would be very interested in that. So please contact me. I think you can. Yeah, I can give you my email address, or you write to contact@fmi-standard.org. What I think this could be a layered standard. Yeah, it sounds really interesting. There's also some similar activities in the field of this SSP standard. They have a standard for. They are currently developing also a layered standard for the traceability of simulation. So this also goes towards, let's say, credible simulation, and also in the process of creating a simulation model, many steps are. So someone creates the model, someone calibrates it, someone verifies it. So there are certain steps, and there's also certain documentation that would be perhaps good to exchange and perhaps align on this. But yeah, and then nice, if you have such a description, it could very well be of a layered standard. So you say for a given model in some defined folder of this extra subdirectory, you can put this information. So someone that gets an FMU, he gets also this additional information. Yeah.
No, it sounds very interesting. We'll contact you, and we have even the term of design contract. You also mentioned a contract between a modeler and the user. So we are on the same ship, I think.
Awesome. I'd love to be part of the meeting, by the way. So let's get that done. A quick question from my side. What's in store for FMI 4.0 or 4, I guess? Any crazy ideas that already?
Oh, we hope that we don't have to do it. So let's say FMI 4 is far away. So we also for the FMI standard, we need stability. So as we saw for FMI 2, currently is the adoption phase. So in FMI 2, it took several years. I think with FMI 3, it will be faster because let's say the infrastructure is much better. So for example, we have several checkers for FMUs, we have reference FMUs, we have now this compatibility information and so on. So I think there will be a faster adoption. Even we now already have 25 tools supporting FMI3, at least partially, only let's say 1 year after the release. Also with big players like MathWorks now supporting FMI3, I think this will get faster, but no one currently wants to do an FMI4. So the goal is more to have, I can perhaps more comment on the FMI 3.1. There we currently think of more efficiency topics. Now that we have binary data and arrays, currently lots of data is copied around several times. And so this can be either for large data and also for if you have lots of scalar variables. Also internally, the data might be organized differently than it's exposed to the outside. So this can also be not efficient. So we currently are thinking for FMI 3.1 to concentrate on such efficiency topics. And this would also be very interesting if you have use cases where you face efficiency topics that are based on the data exchange. We would be very interested in these use cases because we then can consider it for the design of FMI 3.1. But for the FMI4, this is beyond our thinking currently.
Yeah, fair enough. It's very interesting always to follow along with FMI. One problem that we ran into in the maritime industry is that you have get some microphone feedback. You have to deal with wave spectrum on the ocean, and that often means that you have to at least exchange, let's say, 16,000 plus components for every time step if you want to realize the wave spectrum. So quite early on we realized that we would love to have arrays with FMI. So it's good to see that those came.
Yeah. So I think this can be realized with arrays or with binary data if you define a certain MIME type for that. There were already for FMI2, there were some hacks. There were people, so for example, for simulating sensors, there was this OSI standard with this OSMP, OS something for model packaging. They had a hack where they exchanged more or less integer values to transport a pointer where the data lies and so on. But now you can do it nicely with FMI3, so one should not go for these hacks. But I think with FMI3, this is a good use case, yeah. But it would be also, it's also perhaps really an interesting use case where we have such large data exchange. So if you face their efficiency problems, or it would be very good if you could send us this information, yeah.
Awesome. I'm afraid we have to move on, but thank you so much for taking your time. Warm wishes to Southern Germany, and well, have a great day, and looking forward to that meeting, of course.
Yeah,
right.
Thank you
Thanks
for having me. Have a good conference.
Before Hans-Peter is on as our next speaker, Knut Tore wanted to, but you can of course come forward, Hans-Peter, and get set. Hans-Peter's gonna be, sorry, you will go first, of course.
Just forgot some announcements. First of all, if there is somebody that doesn't have their name card, now they are put here. It's always nice to see who people are, so just grab those. And another thing I forgot in the beginning, we figure out that taking this co-simulation to the next level, it will be a lot of late nights, basically. So for the speakers, we got some coffee. So
that will be a good time for the previous speakers to come back again.
So at least you, Tim, get one here, and Bjørnar will also have one. And there's even one for you, Severin. It's local coffee made by one of our startups, or the beans are probably not from here, around here, but at least, yeah, you got the point.
Okay.
Yes, Hans-Peter, I think you're going to have the difficult task to take all the abstract technological things and ground us a little bit more with telling us a little bit about the Møre Ocean Lab and experimentation.
Thank you. Yeah, my name is Hans-Petter Hildre. a professor at NTNU just across the street here in Ålesund. I should talk about Møre Ocean Lab, but I will be into a few comments about digital twins and co-simulation in the end. I know I'm between you and the lunch, so I will hurry up. So this is what we are going to build in Ålesund, just outside here. We are going to instrument the ocean outside here, instrument ships, instrument the sea bottom and the floating structure. And the idea is to make benefit of this type of instrumentation into our research, education, innovation, and business. I will be back to some details about this. You have to, I don't know why. Yeah. We know that in Trondheim they are building now a huge laboratory for scale testing. 10 billion NOK project, and I think this will be really state-of-the-art facilities for research and education in Trondheim at NTNU. I will be into full-scale testing, how we can also do testing in full scale in the ocean. Yeah. I hope you are not hungry. Yeah. And this is about data. And if you are available of data, look at the top corner, the number of sensors on the internet. They count it in zeta, 10 in power of 21. And now they have to count it in iota, that is 10 in power of 24 something. It is a huge development of sensors and sensor systems and how we can make benefit of these sensors into our design, engineering, and how we operate things. Yeah. We can see the same development in smart cities all over the world, and we can see how this is development also as a part of Offshore Simulator Center here. Huge development of sensor, how to bring it into operation, design, and so on. And also in the ocean, it is project all over the world, how to do instrumentation in the ocean, in the seabed, on the surface, and so on. Okay. Now it is working. This is what we pretty much have already today. We have a remote operation center and building infrastructure and how we retrieval of data and so on. This is the development what we are going to do in the next 2 years, in 24 and 25 pretty much. We have already the ship Gunnerus, and we are going to order a workboat next week, and we have building a lot of platforms of autonomous vessels drones, and also a harbor for this. And after that, we are going to do this instrumentation part, buoys, ADCPs, echo sounders, and all this type of equipment and sensors in the ocean. So we are now building these standards, this platform first, and then we are adding this type of instrumentation in the years to come. Isn't this nice? Yes. And we are also into making this control center of all these sensors, so you can have available to all sensor data, but you also can control and do control of these autonomous ships and so on. This is the location outside Ålesund, and we can see where we are going to locating. We will have this ship, autonomous vessel that can go everywhere. The Statens Vegvesen do already have a lot of sensors in this region, and here's a ferry key we are going to instrument the Vartdalsfjorden, that is for hydrophone, sound, and all these instrumentations. And here we have radar station, and at Godøya and into harbor, and so on and so on. And you can ask, why in Ålesund? Isn't that a good question? It is one of few places that we have very open sea just outside here, hurricanes and bad weather, but we also have sheltered areas, and we have fjords, so we can go from this depth to 700 meters sea depth in very short distance. So we have pretty much a huge ocean in a very condensed area. I think that is very important. And we have many, many actors in this region as well. And actually, between 1% and 2% of all the fishes we are fishing every year is born just outside here. First of all, the herring and haddock, actually. So this is a very nice area to have an ocean laboratory. And we have the rivers and fjords and so on. And actually, it is quite nice here, isn't it? And we have a very accurate map of the seabed on the place in Norway with a very accurate map on the seabed. We have also a map of what is on the seabed, sand, stones, and so on. So it is quite a unique area we do have. And if you're going to do autonomous vessel control, this is 1 month in February 27. This is the fishing vessel traffic. So if you are going to do research on autonomous vessel, this is a nice place because there's a lot of traffic in this area. Now you will have lunch, so I will just look at this as a film. I will just browse it like this. This is areas that we believed and we can do into our research and development. From energy and to floating offshore wind, we can do such testing and verification in these areas. Subsea lifting is 700 meters sea depth, subsea installation. It is type of investigation that we can do in this ocean and area. Lifting operations, and all these things. Maneuvering, ship in variety of conditions, and so on. So this will be a full-scale laboratory in this region. Fishing, spinning rod, and so on. Remote operation center, we are building it. Kongsberg showed their remote operation center looking like this. And we are also doing auto docking of ships and so on and so on. Fish farms and all these things. I will jump there. Was it too fast?
No, it's good.
Still good, but I'm not finished. Okay, I will step a little bit into some project we are doing, into digital twin technology, and also some in machine learning. We have a lot of talking about simulation and simulation models. Then we have a long number of assumptions. We are assuming the weather, we are assuming the situation, and we are assuming the boat behavior and so on. What if we can move some of this simulation that is done a year before the operation into the ship, into the real time just now? The ship is in place. I think you asked the questions about doing remote and simulation at the same time. We are doing it. We have been doing it with Gunnerus a long time, and I explain what we can do. If we can move this simulation on board the ship, closer distance between simulation and real operation. You can do the simulation setup a year before, but then you can reuse it in operation. Then the assumption is much less because you know the weather condition, you know the current, you know the situation, you know a lot of things. So you are reducing your assumptions in the simulations. Just by adding all this information from the real operation, then you have pretty much a digital twin. You are adding information from the ship, from the ocean, waves, current, wind, everything into the simulation model. Then you have a digital twin, and you can redo the simulation with much more accuracy of what is going to happen. So this is what is possible. And then you have a kind of decision support. You can support your operation and your behavior and what you are doing. Isn't it nice? And this is possible. We have been testing and done some verification of this type of thinking. But then a simulation model with sensors from the real system, from a physical system, then you have this digital twin. That is the difference between simulation and digital twin. We have been doing this, and 2 weeks ago, we was 1 week just with Gunnerus outside Ålesund and collecting data, because we have a dynamic model of a ship, how it behaves, but there's always they are not always very accurate. First of all, the damping is not accurate and so on. And the ship are loaded different. The center of gravity is different. All these things are different. And then we are using machine learning when the ship are in operation to learn and do a compensation of the mistakes or the small errors in the ship model. In a few weeks, we will test and verify. We have done some tests of it, but now we are collecting data, so we will do this type of investigation. Quite smart way to reduce errors in your models. The next step we are into just now is prediction. By a wave radar, you can see 2 minutes ahead of you. What you can see, you can turn into waves, and into waves that is going to hit the ship. And it is possible to predict the ship behavior, role of the ship in the next 2 minutes. We are not there, but this is what we are getting into just now. So when you are doing critical operation, you can predict how the ship will move in the next 2 minutes. Like a ship for offshore wind, you are going to move people from the ship to these wind turbines and so on and so on. You can predict what will be the ship movements and so on. Nice? Very nice. So all this, and we can do docking support. You can see this ship. The weather forecast in the open sea is quite accurate. We know the wind out there, we know the waves out there, but in this harbor, it is completely wrong. Because if the wind is from this direction, it is no wind there, and it is no waves. We know that. So just by instrumenting this area and add machine learning for 1 year or something, we can be able to predict very precise, exactly to do docking and such type of local operation in a very accurate way. So by having a wave radar and buoys, you can learn exactly how this is. And this is accurate. You have some buildings, so when the ship is here, it is blowing, not blowing. Over here, it will have a lot of wind and so on. And even the ship can communicate with this digital twin, telling exactly how to do the docking for autonomous vessels. Nice. Last thing, I also have to say something about co-simulation since I'm here. And we did a lot of testing of this, and the most challenging task we could imagine, this is a huge thing, lifting these turbines from height higher than the turbines. We had a concept. We can lift only from the lower point. All the weight is just down here, so we don't need these cranes. And we have a kind of pivoting balancing point up here, so it is not tilting. And we have wires, and we have winches, and so on. Is this possible to do by co-simulation? And I will just, sorry for this. Then we have two bodies, that is floating bodies. The ship is controlled by thrusters and DP system. We have a spar that is connected to seabed, not connected, but anchored to the seabed. So we have two floating structures. We have hydraulics and hydraulic system, wires and control system. So this is a multidiscipline type of approach. Could we mix this multidiscipline approach together? And we made this modular way of thinking to have all these models from the spar, the ship, DP system, DP control, winch control, and so on. And we did use this type of setup and this type of equipment. We did use OSP. We have a local version of this at NTNU that is only some extra functions, but it was the OSP framework that was used. And we have a lot of learning in this, of course, because this is a challenge to mix all these models together. And also to understand these stiffness issues, to have not numerical problems, but we also have stiffness challenges and understand stiffness from control systems to hydraulic systems and so on. But finally we did it. Last page. I think this use of real-time data from all the sensors will change how we design and operate ships. I think this is a key to go also into this digital twin. And digital twin and machine learning will be a key technology to achieve this. That was my final takeaway of this. Thank you.
Thank you very much, Hans-Peter. Couldn't agree more with that slide. Also, of course, technologies are not excluding, but supplementary. So both technologies are also very interesting if you see them in the context of co-simulation. But not everything is co-simulation, as we've heard, rightfully so. I'm in a difficult situation because there's a bunch of people, including myself, that's very hungry. We are behind schedule and we have to start in time again. I'm wondering if should we allow one question, or should I tell them to talk to you directly? Maybe one question would be okay, wouldn't it?
That is okay. If not, you can grab me at the lunch.
Or shall we just do the latter one?
Let's go for the lunch.
Okay, let's go for a lunch. If you have a question or comment for Hans-Peter, he will be also having lunch with us. Thanks for now, and we'll be back. When will we be back? That's maybe also a good thing to mention. I feel like I should have a good overview of the agenda, shouldn't I? Yes, 10 minutes after 1 o'clock, back here we start up again. Thank you very much for now. All right, looks like everybody was done and ready to go before me. Sorry for that. Welcome back. Microphone doesn't want to cooperate. Welcome back. Hope you had a nice lunch. Fortunately, a little bit shorter than we had anticipated, but that's how these things sometimes go. Off to the next part of the conference. Siegfried and Roger from DNV are going to tell us about model lifecycle and conceptual models. Very exciting, interesting. A little bit of the nerd talking, but it is very interesting, also for non-nerds. And after that, we're going to have a panel debate, so that's also going to be very interesting. So,
thanks a lot. Yeah, let's go a little bit towards assurance, which was mentioned several times today. And actually, it's not about nerd. It's about people talking about models. This is a quite normal life cycle of modeling, not invented by us, used a lot in our assurance recommended practice. And it talks about this reality where we want to have some features modeled, a conceptual model, some, let's say, an intermediate stage. I will talk a lot about that today. And then the model itself. And as we say it's actually the thing everybody does. So it's not our invention and everybody does it. But it's this confusion about verification, validation, which often goes wrong. We do premature jumping to conclusions, to models, not jumping a little bit over this conceptual thing without thinking it, finish thinking about it. We think only function based. Oh, I'm so glad that I managed to get this function working, and not about what can go wrong. It's not systematic, and it's not conscious enough. It's only in the back of our head somewhere. We have thought about it in the night, right? And now and day after we start modeling, not writing down what we thought, and not discussing it with all the stakeholders of the model. And that is something we see creates a lot of problems. We have late and no detection of problems. We have too many iterations because something went wrong and okay, let's start again. And we think that software is easy to redo, but it's not cheap to redo. I mean, we need to do some iterations and we want it, but to do too much about it is expensive. So our thinking is if we do this cycle in a more conscious way and in a more qualitative way, in a better quality way, I want to say, then we can even do models cheaper and more to the point, getting to the good results quicker. That's our vision, at least. It remains to be shown, but I really believe in that. So, the use case, one very important example, and I would really state this here. A model without a use case does not make sense. It's actually not a model. If you don't have a use case, you have only the reality to cope with, which I copied here, and that's not a model. You don't want the reality. You want a model. You want some features focused on, and that's the use case, right? So therefore, be conscious about that. We need to identify stakeholders. Who else is? It's not only the modeler. Very important. It's actually the user of it. It's maybe the money giver. It's the bigger system, which is a stakeholder, not only the component, right? So anybody who has anything to do with this model should be involved. And then together with these, identify what is this really to be used for, because only then we can define what we need to include and what not. So, in a way, go away from this reality to the conceptual model. That's the thing which needs to be done. High-level limitations and assumptions, they start there, right? Because if you are not talking about the reality, you talk about assumptions and limitations, and these needs to be collected, and everybody needs to know about it and agree. So these discussions with stakeholders, they should really also go in normal language, not using any kind of modeling language for that. It's Norwegian or English, German maybe. And then also this high level risk analysis, which should be started at that point, because just this thinking, okay, I want to put all this functionality into the model, but what can go wrong? I have done many risk analyses and collecting the people around the table, doing a cruise line or whatever, and they get more and more annoyed with me. We made these nice functions and you only talk about what can go wrong, right? More and more annoyed until we find the first problem and the next problem. And oh wow, yeah, things were not in order. And then I have them on board and then sitting in this shipyard and even the future captain uses the time to be there every day doing this risk analysis, because this gives me valuable information, what can go wrong, how should I handle my ship when things go wrong, right? So then that's really fun when people get on board like that. And that is what it is about, this risk analysis. Maybe I find time to show you an example of that. Yeah, so what happens when the model does not perform adequately? That is our normal thinking about risk analysis. But that is not a problem when it's evident, right? If a functionality in a model which we want is obviously not there, that is a deficiency. It costs you money because you need to do another round to put the functionality in. And if you detect it late in the process, it's really annoying and may even break the project because it's too expensive. But it's not really the problem we are concerned about. What we are really concerned about is something is possible which turns out to be wrong in reality. That is not good, right? If the model fools you towards believing that something is possible, which is actually rubbish. And even worse, if something unsafe cannot happen. So the model tells you, oh, well, that's fine. No fires, yeah? Not possible to have fire, but reality tells you differently. And if you then detect that too late, that's really not good. So these last two things should be the focus of any risk analysis of a model. How can the model fool me? I don't want to be fooled, right? I want to know. That's why we make the models. So here in our recommended practice, we have this section about conceptual model qualification. And that is basically the content of what we want to have inside that. The objective of the model shall be there, a clear boundary, what is inside and what is outside of, let's say now, a component model, an FMI, yeah, right? If I want to make an FMU using the FMI standard, then this would be the question: what should I have included inside? What do I expect outside of my boundary? You start to collect requirements, the modeling concept. So what we mean here is, okay, is that hydrodynamics simulation type, or is it some kind of discrete event simulation, maybe? So all that needs to be clarified and discussed with the stakeholders so that we all agree, yeah, we need this level of detail, therefore we need this type of simulation. starting to collect assumptions and limitations, as said, very important, and it's also important that we grab them while we have them, because it's so easy to forget assumptions later on in the project. So when an assumption is identified, write it down and have it at a central place, so that everybody has access to read it and also to put new assumptions. Because when you start to make the model itself, then new assumptions will turn up. Okay, you need to make a decision. Maybe you can't collect the whole team to agree on it even, right? So the modeler makes the decision, puts it in the assumptions, and later on you do a review of the assumptions, and do we still agree? Oh no, now you broke the whole thing, right? That is not good, but it's much better to know about it than not to know. Risk analysis, as mentioned, maybe you can go a little bit into that. Validation, mentioned here already, validation and verification, so the planning should be done at this early stage, even involving the stakeholders. One reason is that it needs time to collect the data from the real system, where we can relate to and say, okay, yes, this model does just what we want. If we don't start collecting data, we have no oracle, right? So, and all that we want to collect in this design contract. It's a contract between the modeler and the user of the model. I give you that if you obey these rules and limitations. And if you don't, you have not, but I don't give you that, right? Sometimes I explain that with this medicine. If you go to the pharmacy, you get medicine and a leaflet. Nobody reads it. We want these to be read and used. Maybe in time, we hope that we get tools so that what is written in the design contract can even be used for automatic testing. If we can make them machine readable, that's what we discussed with this FMI 3 guy. So let's see how we manage. So yeah, so that would all be into this conceptual model. We are also currently making tools to do that. It's not ready, but we see that it would help a lot if we had good templates and tools so that people can get started with this conceptual model thing. We see, maybe Roger will get into some examples there. It goes often wrong, and that's not